Well, good day, ladies and gentlemen, and we are in our discussion on galvanic cells and cell potential. And today we want to get into this idea of spontaneity. So before we get into that, let's talk a little bit about our cell potential, right? Last time we learned about a cell potential, and we said, hey, I can calculate a cell potential, meaning I can calculate the electromotive force which is driving my galvanic cell to operate, to function, by looking at something called standard reduction potentials. And that would mean we look at something like, yeah, I don't know, copper 2 plus 2 electrons going to copper solid. This is aqueous here. And this would have a standard cell potential. It is a reduction reaction, and so it's going to be a potential for a reduction reaction. And standard just means that we have what? 1 molar, 1 atmosphere, and 298 K are the conditions for this standard. And we said that we could calculate our cell potential by looking at each half cell, and we could say, hey, the cell potential is the standard reduction potential at the cathode minus the standard reduction potential at the anode. And what is happening at the cathode? Well, that is my half reduction reaction or half reduction cell. And at the anode is what? My half oxidation reaction, right? And so my cell potential is the standard reduction potential for the half reduction reaction minus the standard reduction potential for the half oxidation reaction. And we can calculate that using some tables. Good. Moving on. So now let's take a look at this dog. It says the following redox reaction, blah, blah, blah. What is the E for this reaction? Is this reaction spontaneous at standard conditions? Okay, we want to go back and revisit this idea of spontaneous. So let us go back up here, and I'm going to clean this off a bit, and we're going to start some notes, all right? Good. So let's start off with this idea of spontaneous. Good. So what is spontaneous? Well, a spontaneous process, let's talk about a spontaneous process. That is a process which occurs eventually. That's the key word on its own. Oops. On its own. There we go. It is a reaction that eventually occurs. Does it mean we can see it? No. Does it happen fast? It might happen fast, might happen slow, but it will eventually occur. And another way to think of this is what the AP people call, this is a process which is thermodynamically favored. That's their term now, thermodynamically favored. Good. So it's a process that is thermodynamically favored. For most of us, it's the idea of a process which occurs eventually. Now, my only suggestion on this is do not confuse kinetics with thermodynamics. This question, thermodynamics, spontaneity, is all about this question. Let me give us some more space down here. Spontaneity is all about the idea of will it happen? Will it happen? That is spontaneity. Kinetics, that is how fast will it happen? If it will happen eventually over 1,000,000 years, then it is spontaneous. If it happens fast, we say, that has to, will it happen fast or slow? That has to do with kinetics, okay? So will it happen on its own? That is spontaneous. Some things some things are spontaneous and we cannot see them happen because they have a very high activation energy, and so we don't see it happen unless you can overcome that activation energy with something like a spark. Okay, good. So that's spontaneous, and we can calculate spontaneity using our E cell, right? Or E, let's just go with E prime, right? With E prime, or really with just E, right? If E is positive, then it is the forward reaction. We're going to forward reaction is spontaneous. If E is negative, then the forward reaction is not spontaneous, right? Good. That would also imply what? If the forward is not spontaneous, that means the reverse is spontaneous. Good. And we said, hey, I can calculate this E prime for a cell, right? I can come down here and I can calculate it for a cell. And if it's, excuse me, an E, if it is at my standard conditions, we'll call that an E prime, right? So I can get my standard cell potential, which we just said is equal to my standard reduction potential at the cathode, minus the standard reduction potential at the anode, right? Cool. And that's for a galvanic cell, but what is really cool, which is more cool or additionally cool, is that I can calculate this for any redox reaction. So for any redox reaction, we can calculate an E, a standard potential, and that standard potential is going to be equal to the standard reduction potential of the reducing species minus the standard reduction potential of the oxidizing species, right? All right, cool. So let's do that. Let's go to our next slide, and let's take a look at this. I have a redox reaction. I have copper going to copper 2 and hydrogen cation going to hydrogen. Now, here's what we have to do is I have to determine which of these is oxidizing and reducing. So what is reducing here? Well, I have copper 0, and this is a +1, and copper 2 plus, and hydrogen 0. So it looks like my hydrogen is going from 1 to 0, so it is reducing. So my H plus is my reducing species. My oxidizing species is my carbon, and not my carbon, my copper. And we said what? My E prime, my standard voltage, is equal to my standard reduction potential of my reducing species minus the standard reduction potential of my oxidizing species. Notice we have to use a reduction even though we are talking about my oxidizing species. So that means I have my H plus, two H pluses plus yoink, yoink. I have two H pluses plus 2 electrons going to H2. And I have to write this as a reduction. So copper plus 2 electrons going to copper, right? And then I can look up the standard reduction potentials. I have to write this as a reduction, even though it's oxidizing here, because my table is all about reducing species. So let's take a look at my table. There it is. My hydrogen should be 0. Ooh, look at that. No, 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 no. Hydrogen is 0. And copper 2 is, where's my copper 2? Right there, 0.337. Okay, let's calculate that. So let's go back here. So E prime is equal to my standard reduction potential for my hydrogen, which is 0, and we said 0.337. Is that right? Good. So this would be 0 minus a 0.337, and that gives me a negative 0.337 volts. So that is my potential. Now the next question is this reaction spontaneous? Well, it's a piece of cake. Is this positive or negative? It is negative. My E prime, in this case, is less than 0. That means it is not spontaneous. It's a forward reaction. Good. Piece of cake. All right, you guys try the next one. Bring me back when you're ready. There we go. All right, so first thing I have to do is figure out what is oxidizing and reducing. 0, -1, going to 0, and -1. Looks like my chlorine is reducing, and my iodide is oxidizing. So that means I'm going to have my E is equal to the standard reduction potential for my chlorine minus the standard reduction potential for my iodine, right? So good, here we go. So I have I have my chlorine plus 2 electrons going to 2 chlorides, and that will have a standard reduction potential. And then I have my iodine plus 2 electrons going to 2 iodides, because that is reducing there, right? Good. Now let's look at our table. Chlorine and iodine. So where's my chlorine? Chlorine. Nah, 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 nah. Looks like chlorine is a, where is it? Chlorine. 1359. Okay, 1359. 1359 is my chlorine. And what's my iodine? Iodine is right up here. It looks like a 0.536. 0.536. Okay, so let's go back to our question. Zoink. We said this is 1.359 volts, and the other is 0.536. Let's plug it in. So I have 1.359 minus 0.536. And what do we get for that? 0.1359 minus 0.536 equals 0.83. Nope, no, 0.823 volts, and that is a positive. Since it is positive, that means this reaction is spontaneous. It is spontaneous. Great. Okay, now there's another thing that we can do to calculate, another way to calculate spontaneity, and this is the idea of something called delta G. So let's take a few notes here on my delta G. We want to talk about this thing, delta G. So we're talking about spontaneity, spontaneity, or spontaneous, and we got a definition, and we talked about how E is related to it, and we can talk about this thing called delta G. And delta G is what we call our Gibbs free energy, all right? And it allows us to predict spontaneity. All right. Now, you'll get into this in more detail at some other point. You know, delta G is equal to delta H minus T delta S, my change in enthalpy minus the temperature times my change in entropy. But what is really nice is that if we are at standard conditions, so if we're talking about delta G prime, we can calculate delta G prime using tables. There are things called delta G of formation tables, and these tables allow us to calculate delta G prime, and the way we do this is delta G prime is equal to M times delta G prime formation for my products minus N delta G prime F of my reactants, where M and N are my coefficients in the balanced equation. All right, so that's the way I can calculate delta G prime. And here's the relationship between delta G prime, or delta G for that matter, and spontaneity. When delta G is less than 0, then your forward reaction is spontaneous. If delta G is positive, then the reverse reaction is spontaneous. And when my delta G is equal to 0, then guess what? We're at equilibrium. Good. All right. That's what you need to know for my delta G. I think that's all we need to know to calculate to do our question here. So I've got this thing here, and I've got, I want to figure out if this is spontaneous. So I'm going to calculate my delta G prime. So delta G prime is going to be equal to products, right? I'm going to say M times my delta G prime F for my products minus N times delta G prime F for my reactants, okay? Good, so what are my products here? I have PCl3 and O2, so I'm going to take my 2 times delta G prime F for PCl3 gas. Now make sure you get those states because they are important. Plus 1 times delta G prime F for oxygen gas minus, now my reactants, 2 times delta G prime F for POCl3 in a gas. Good. Now we go to our tables and we can plug and chug. So let's find some wonderful tables. I hope there are some wonderful tables here. Yoink! Wonderful tables. Beautiful. Good. So we need PCl3, and that is going to be a negative 269.6. Make sure you're under the right column, right? Because you have a couple other things here. We only want the delta G of F. And we need POCl3 gas. And which one is that? POCl3 gas will be a negative 502.5. And I need oxygen gas. And look at oxygen gas. Woohoo! It's 0. I can handle that. All right, let's plug in the numbers and see what we get. So we come back up here. Oops, sorry, come back up here. And let's lay in some numbers. I need 2 times my PCl3 gas, which was a negative 269.6. By the way, that's in kilojoules per moles. Plus 1 time the delta G of formation of oxygen, so 1 times 0, minus 2 times my negative 502.5 kilojoules per mole. Good. Let's get my handy dandy HP30XA and run some numbers. 2 times 269.6 negative equals that, minus 2 times 502.5, and I get a positive 465.8 kilojoules per mole. Let's make sure I did that right. So 2 times 269.6, yoink, equals negative. That's a negative 500. Minus 2 times 502.5 negative, and that whole thing's going to be positive. Whoops. That's a positive. Oh, there we go. That indeed is the right answer, right? Okay, and so this is my delta G prime, and since it is positive, delta G is greater than 0. That would mean my forward reaction is not spontaneous. Okay, good. You guys try the next one. Bring me back. All right, here we go. Not difficult at all. Delta G prime is going to be equal to what? 1 times my delta G prime of nitrogen plus 3 times my delta G prime for hydrogen minus 2 times my delta G prime for ammonia, and these are all gases. And so we go and look at our table. And let's say, here's my table for that. Oops, I need another table. Let's go down here a little farther. Let's look at this table. And what do we see? My N2 is 0. So here's my N2, 0. My H2 is 0. And my NH3 gas is a negative 16.66. This is an easy calculation. So this is equal to 0 plus 3 times 0 minus 2 times a negative 16.66 kilojoules per mole. And so this looks to me like a 16.66 times 2, and it is a positive 33.32 kilojoules per mole. And it is, since it is positive, that is not spontaneous in the forward direction. Okay, great. That's easy. Moving on, one last thing and we're done. We want to talk finally about the relationship between the two, right? Here's this question. I have a redox reaction, and they want us to calculate our E prime and then get a G prime without using the tables. Okay, let's go back to our notes here. So we were talking about spontaneity, and there is a relationship between E prime and delta G prime. So let's take another line off here, and we have our relationship between E prime and delta G prime, and it is a simple one. It is that delta G is equal to negative NFE, and if all of those are at standard conditions, then that becomes delta G prime is equal to negative NFE prime, where N is the number of electrons transferred in your balanced equation. So you're going to have to look at your balanced redox equation to get N. And F is equal to 96485. And that would be in joules per volt mole. Volt mole. And then my E is prime is going to be in volts, right? And that is our standard potential. Good. That's all there is to it. So let's plug and chug. Let's run this through. Here we go. So we need our last slides. Here it is. Okay. So first thing you have to figure out is how many electrons are transferred. So we have to look at our actual half reactions, right? So I have iron 2 plus 2 electrons is going to go to iron solid. And I have copper solid, and it's going to have to go to copper 2. How does it go from copper solid to iron 2? It must give up 2 electrons. So I have 2 electrons that are lost here, 2 electrons lost or gained here. So how many electrons are transferred? The answer is 2. So I need to calculate my E. So my E is going to be equal to what? Well, it's going to be my standard reduction potential of my reducing species. What is reducing? Iron. So I need my standard reduction potential for my iron minus my standard reduction potential for my copper 2. Good. So let's go back and find those. Let's go and find iron and copper. So where's iron? Copper we already found. Copper is 0.337. What is my iron? Fe. Iron. H-A-I-E-F. Fe. Iron to a negative 0.440. Negative 0.440. Let's run our numbers. Here we go. I have a negative 0.440 for my iron minus a 0.337, and that gives me a negative 0.777 volts. That is my E prime. So what's my delta G prime? Delta G prime is equal to a negative in how many electrons are transferred? 2 times my Faraday's constant, 96485 joules per volt mole, times my standard cell potential, a negative 0.777 volts. And what do I get? 0.777 times 96485 times 2, and I get a positive 149937 joules per mole. And just to make that a little cleaner, let's make that into kilojoules. 1, 2, 3, and I get 3 sig figs. So it's really a 150 kilojoules per mole positive. Good. Is that thermodynamically favored? My delta G is a positive value. My E is a negative value. The answer is no. It is not thermodynamically favored. You do the last one, and we are done. All right, here we go. Let's do this. First thing we have to do is calculate our E prime, and I want to figure out how many moles are transferred, so electrons are transferred. So I have aluminum, and I have I2. My aluminum is going to aluminum 3 plus, and my iodine is going to I minus. Looks like I need 2 electrons here, so I'd have to have 2 there. I have to have things balanced here. And I need to have 3 electrons here, right? And notice my coefficients up here. This says that I have 2 aluminum, so that means this whole thing has to be multiplied by 2. I have to have a 3 in front of this, so this whole thing has to be multiplied by 3. And that makes sense, right? Because now 3 times 2 is what? 6 electrons down here, and 2 times 3 is 6 electrons up there. Good. How many electrons are transferred? The answer is 6. So my N is 6. We need to get my E prime, my standard potential. What is oxidizing? Let's see, aluminum is what? Aluminum is oxidizing. My iodine here is reducing. So I need my standard reduction potential for my iodine minus the standard reduction potential for my aluminum. Let's go check those out in our table. Back here, I need iodine and aluminum. You guys may have those memorized, but I sure don't. Here we go. Let's go find aluminium, a negative 1.66. So we have a negative 1.66. And what's my iodine? That one should be circled. Nope. There it is. A positive 0.536. 0.536. Let's run the numbers. Run the numbers. Here we go. We need more space down here. My E prime is going to be my iodine, a 0.536 minus my aluminum, a negative 1.66. And what do I get out of that? Looks to me like that is a 0.536 minus a negative 1.66. And that gives me a positive 2.196. By the way, that's not significant. That's 6. And now let's calculate my delta G prime, which is equal to negative NF E prime. So this is equal to a negative times what? N is equal to 6 times my F, 96485 joules per volt mole. Might as well memorize that. It's going to be around a long time. Times 2.196 volts. Run the numbers. 2.196 times 96485 times 6, and that gives me a big number, like a 1271286 negative. This is in joules per mole. Let's go 1, 2, 3. And what do we get? We get a 1270 kilojoules per mole negative. 1, 2, 3. Good. There we go. That's my delta G. It is negative, so that means this is, jawohl, spontaneous. And now you are experts at delta G and E prime and spontaneity. Ciao.